Hi everyone! Today we're going to discuss something called the Arrhenius equation. This equation is very useful in chemical kinetics. So previously we discussed reaction rates, and in those reaction rate laws we had something called the rate constant, K. And this is actually temperature dependent. So K does change depending on the temperature of the reaction. Now, the Arrhenius equation shows the relationship between the rate constant K and temperature. So here we have that K, our rate constant, is equal to A, which is called the frequency factor, times an exponential factor. And in that exponential factor, we have negative EA over RT. So EA is called the activation energy for a reaction. R is a gas constant that we've seen before. And T is the temperature. So T has to be in Kelvin because we are using the gas constant R. And R, in this case, will be 8.314 joules per mole Kelvin. And then remember that A is the frequency factor, which is the rate that the reactant approaches the activation energy. So we'll look at a diagram of that in a second. And then EA is that activation energy, which is the minimum energy needed to start a reaction. Okay, so very important equation. Now, this form of the equation might not be super useful, so we'll see other forms of this equation. All right, now before we look at our energy diagram graph that I'm going to show you in a second, we just need to go over a couple of terms. So in all reactions, there is something called an energy barrier. So you can imagine that energy barrier like a hill, where let's say we're driving up a hill. We need a certain amount of gas or energy in order to get our car up and over the hill. And that's the same thing with reactions. Reactants need to have enough energy in order to actually react. And that energy is the activation energy. So that's the amount of energy needed to convert reactants into something called an activated complex. This is also known as a transition state. So an activated complex is kind of the halfway point between the reactants and the products. So it's kind of like where the reactants are starting to form the product, but they haven't quite gotten there yet. So that's the activated complex. And the activated complex will have partially broken and partially formed bonds. And due to those partially broken and partially formed bonds, the activated complex is always really high in energy. So another way to think of it is it's pretty unstable, so it's going to have a lot of energy associated with it. But then once you form the products, it becomes more stable, and the product should be lower in energy as a result. So as an example, let's look at this energy diagram. And this particular energy diagram is for the reaction between hydrogen and oxygen gases to form water as a gas. So initially we have two hydrogen molecules and one oxygen molecule, and they have a particular energy associated with them. So on the y-axis we have energy, And then on the x-axis, we have the reaction progress. So as the reaction is progressing, the bonds for the reactant molecules are going to start to break. So maybe we could draw our activated complex. So you'll notice that the energy of the reactants is going to increase until we hit the activation energy, so that energy that's needed for the reaction to occur. And at this point, we have partially broken bonds from the original molecules and partially formed bonds between the other molecules. So you'll notice hydrogen and oxygen are starting to kind of form a bond there. Now this isn't what it actually looks like. This is just kind of a hypothetical. But eventually we'll fully form our new bonds and fully break our old bonds, and we'll end up with our products, which are two water molecules. And those two water molecules are really stable, so they have a really low energy compared to the energy of the reactants and the activation energy. Now you'll notice that the activation energy is the difference between the energy of the reactants to the top of that hill. So it's not from, for instance, the energy of the products to the top, it's just from the energy of the reactants to the top. Now another example is the isomerization of methyl isonitrile. So methyl isonitrile is shown on the left, and it can rearrange into a new molecule called acetonitrile. So you'll notice that the only difference between these two molecules is the carbon and the nitrogen have switched places. So both of these molecules are called isomers because they have the same atoms, they're just arranged differently. Now, in order for this reaction to occur, again, we need to add some energy. So there will be an activation barrier. But additionally, we have to break the bond between CH3 and nitrogen. And then we have to form a new bond between carbon and CH3. So the activated complex, or kind of that midway point between reactant and product, involves that carbon-nitrogen group, shown here, rotating. So that group is just going to kind of flip 180 degrees and form a new bond. So this is the energy diagram for the reaction, or the isomerization of methyl isonitrile. So at the beginning, we have our bond between CH3 and nitrogen, but then it starts to break once it has enough energy, and then we get our activated complex, where that carbon-nitrogen group is going to flip, and the amount of energy needed in order to do that is the activation energy. But once that group flips and we form our product, then we're suddenly at a much more stable point, or at a lower energy point. And what's interesting is the difference between the reactants and the products. So the difference between their energies is equal to the enthalpy of the reaction. So this kind of goes back to our thermodynamics discussion from last quarter. Okay. So again, remember the activation energy is the difference in energy between the reactants and the activated complex. And remember, the activated complex has a lot of energy because it is so unstable. Now, earlier we talked about that frequency factor. So the frequency factor is the number of molecules that begin to form the activated complex in a given period of time. So how many molecules are actually going to make it past the activation barrier? Our frequency factor will tell us the number of molecules that can start to form the activated complex over a certain period of time. All right. So for this particular reaction, the isomerization reaction, the frequency factor will represent the rate at which the carbon-nitrogen part of the molecule wags or vibrates side to side. So how many molecules are actually going to gain enough energy in order to potentially form the product? That's our frequency factor. All right, so remember that the Arrhenius equation told us that K is equal to a frequency factor A times an exponential factor which has negative EA over RT in the exponent part. And EA was our activation energy, R was the gas constant, and T is the temperature. So if we just isolate that exponential part of the equation, that will always be a number between 0 and 1. And that represents the fraction of reactant molecules with sufficient energy that can make it over the energy barrier. So the frequency factor tells us how many molecules can kind of start to get to the activated complex. And then the exponential factor tells us how many molecules actually make it over the energy barrier. Now, of course, the higher the energy barrier, the larger the activation energy. And that means that fewer molecules will have enough energy to overcome that activation barrier. So for instance, if we have a curve like that versus a curve that looks like that, it's going to be much more difficult for molecules to jump or make it over the red activation barrier versus the blue activation barrier. So the activation energy for the red curve is going to be much greater than the activation energy for the blue curve. Now, another way that we can affect the activation barrier, we can increase the temperature. So if we increase the temperature of a reaction, that will increase the number of molecules that have enough energy to overcome the energy barrier. So increasing the temperature will increase the reaction rate. So on the right-hand side, we have a graph showing a blue curve at temperature 1, and then a red curve at temperature 2. So at temperature 2, we have a greater temperature. So T2 is greater than T1. And you'll notice that the curve has shifted over slightly because there's a higher temperature. So that higher temperature lowered the activation energy. But additionally, if we look at the right-hand side of those curves, as the temperature increases, the fraction of the molecules with enough energy to surmount the activation energy barrier also increases. So on the y-axis here we have fraction of molecules, and you'll notice that the fraction of molecules that made it over the barrier is much greater for T2 versus T1. So increasing that temperature will increase the number of molecules that can become products. So I mentioned earlier that there was a different form for the Arrhenius equation because the form we saw earlier can be a little complex in terms of calculations. So instead, we can rearrange the equation to give us a linear form, where the natural log of the rate constant, K, is equal to negative EA over R times 1 over T plus the natural log of the frequency factor A. So again, this is in the form of y equals mx plus b. So what we can do is plot the natural log of k, which is y, versus 1 over t, which is x, and that's going to give us a straight line. So we'll end up with a graph that kind of looks like that, because our slope will be negative. And the slope, m, is going to equal negative EA over R, the gas constant. So, for instance, if you have a lot of different data points at different temperatures, you can plot the data and then use the slope to figure out what the activation energy is. Or you can figure out where the y-intercept is, and the y-intercept is equal to the natural log of the frequency factor. So you could also figure out what your frequency factor is. All right, so let's look at an example problem, and this is from your textbook. So the decomposition of ozone is important to many atmospheric reactions. So down below you can see that ozone, O3, is decomposing into oxygen and then just pure elemental oxygen, just a single oxygen atom. So a study of the kinetics of the reaction results in the following data. So we have temperature in Kelvin and a rate constant in inverse moles per liter per second. And we're increasing the temperature 100 Kelvin each time, and then measuring the rate constant each time. So we want to determine the value of the frequency factor, remember that's A, and then the activation energy for the reaction, which is EA. So the first thing we need to do is plot the data. So again, we want a graph of the natural log of the rate constant K over inverse temperature. And we should see something that looks like that. Now, luckily, your textbook already did this for us. So this is our resulting graph. And they're also showing the equation for the graph, which is y equals negative 1.12 times 10 to the fourth x plus 26.8. So if we need to find the frequency factor and the activation energy, we have everything we need. We just need the slope and the y-intercept. So let's start by solving for the activation energy. Okay, So we said that the slope, m, is equal to negative EA over R. So let's just plug in the slope, negative 1.12 times 10 to the 4th. And the unit for that is actually K, so Kelvin. And then we're going to set that equal to negative EA over the gas constant, which we said was 8.314 joules per mole times Kelvin. So now we just need to rearrange and solve for the activation energy. So negative 1.12 times 10 to the 4th Kelvin times the gas constant, 8.314 joules per mole Kelvin, will equal negative EA. All right, so if we solve for EA, we do have negative signs on both sides of this equation, so we could just multiply both sides by -1 to get rid of those negative signs and make them positive. So the value of EA is 9.31 times 10 to the 4th joules per mole, because Kelvin will cancel. So notice in our units, we have Kelvin in the numerator and the denominator. So we're just left with joules per mole. Now, we can take this a step further and write this in terms of kilojoules per mole. Typically, activation energies are given in kilojoules per mole. So that would just be 93.1 kilojoules per mole. So we're just going to divide by 1,000. Now, what about the frequency factor? So remember that the y-intercept, b, is equal to the natural log of the frequency factor. So our y-intercept is 26.8, and we're going to set that equal to the natural log of a. And in order to solve for a, we have to take the inverse natural logarithm, so that would be e to the 26.8, and we'll set that equal to a. And that is going to equal 4.36 times 10 to the 11th. And that is our frequency factor. Now, the frequency factor will have the same units as the rate constant. And earlier, we saw that the rate constant had units of inverse moles per liter per second. So our frequency factor will have the same units. So we can just write that next to our value. Okay. Now there is another form of the Arrhenius equation. This is kind of similar to the Clausius-Clapeyron equation that we saw in Chem 162. So this is the 2-point form, and if you only have 2 data points, so 2 temperatures and 2 rate constants, you can use the following form of the Arrhenius equation to solve for the activation energy, or maybe if you have the activation energy, you could try to solve for a rate constant or a temperature. Now, remember with our 2-point Clausius-Clapeyron equation, that was not as accurate because we were only using 2 data points. It's always more accurate to use as many data points as possible. However, if you're in a bind, this works and gives you a pretty good estimate. So let's use this form of the equation where the natural log of K2 over K1 is equal to the activation energy over R times 1 over temperature 1 minus 1 over temperature 2. So in your textbook, there's another example where we're going to use this two-point form. So consider the reaction between nitrogen dioxide and carbon monoxide. The rate constant at 701 Kelvin is measured as 2.57 inverse moles per liter per second, and at 895 Kelvin is measured as 567 moles per liter per second. Find the activation energy for the reaction in kilojoules per mole. Okay, so maybe first, let's just list out what we know. So we have an initial temperature of 701 Kelvin and an initial rate constant of 2.57 inverse moles per liter per second. And then our second temperature is 895 Kelvin, and our second rate constant is 567 inverse moles per liter per second. And again, we want to find the activation energy. So let's write out that two-point form for our Arrhenius equation. Oh, my pen stopped working. There we go. Let's see, so it's T1 minus 1 over T2. All right, so let's plug in everything we know. So K2 is 2.57. K1 is, oh, whoops, I already messed it up. I flipped my K's. All right, so K2 is actually 567. And then K1 is 2.57. Okay, and then we're trying to solve for the activation energy, so we'll leave that as EA. And then we're dividing by the gas constant, 8.314 joules per mole Kelvin. And then we're multiplying by 1 over temperature 1, which is 701 Kelvin, minus 1 over temperature 2, which is 895 Kelvin. Okay, so we can probably already see that units are going to cancel on the left-hand side, and they should also cancel on the right-hand side. So Kelvin for the gas constant is in the denominator of a denominator, so it would actually be in the numerator. And then for the temperature values, Kelvin is in the denominator, so those would all cancel. Okay, so now on the left-hand side, we should end up with, let's see, a value of 5.40. And on the right-hand side, we should end up with a value of 3.09 times 10 to the negative fourth. Okay, so now if we calculate and rearrange to solve for EA, we should end up with a value of 1.5 times 10 to the second kilojoules per mole. So I encourage you to make sure that you get the same answer. And one thing that I usually do is put parentheses around as many values as possible in my calculator. That way the calculator knows exactly what I'm trying to calculate. Because sometimes, for instance, if we're subtracting two inverse temperatures, and we don't put parentheses around those inverse, or like 1 over 701, and then separately put parentheses around 1 over 895. Sometimes the calculator gets confused, so just make sure you're using parentheses. All right, so one thing to also check for is activation energies tend to range from tens to hundreds of kilojoules per mole. So we have 150 kilojoules per mole for this reaction, so that does make sense. Now let's work on worksheet problem 5. So the rate constant of a reaction at 32 degrees Celsius is 0.055 per second. If the frequency factor is 1.2 times 10 to the 13th per second, what is the activation barrier? So what is the activation energy? So for this problem, the easiest form of the equation to use is probably this one, where the natural log of K is equal to negative EA over R times 1 over T plus the natural log of the frequency factor A. We don't want to use the 2-point form because we don't have two sets of data here. We only have one. And then we don't want to use the original form. That's just a little too difficult to solve for algebraically. So this is probably the easiest one. All right, so let's plug in everything that we know. So we're told that the rate constant is 0.055. So we'll plug that into our K value here. And then we don't know what the activation energy is, so we'll leave that as EA. But we do know the gas constant. And then we're also told the temperature. But the temperature is in Celsius, so maybe we should quickly convert that to Kelvin. So remember, if you're converting from Celsius to Kelvin, we want to add 273. You could also add a 0.15 onto there, but this should give us 305 Kelvin. So let's plug that into our equation. And then we're going to add the natural log of the frequency factor, which is 1.2 times 10 to the 13th per second. All right, so I'm going to rearrange this slightly. So remember, if you subtract two natural log values, you're really dividing those values and taking the natural log of that. So if I move the natural log of the frequency factor over to the left-hand side of the equation, we are subtracting it. So we would end up with the natural log of 0.055 over 1.2 times 10 to the 13th. Now, you could also just subtract the natural log of 0.055 and the natural log of 1.2 times 10 to the 13th. That will give you the same exact answer, but in this form, it's easier to see that our units cancel. Okay, so next we're going to set that equal to negative EA, and that's over the gas constant times 1 over 305 Kelvin. And here we can also see that units are canceling, so Kelvin will cancel. All right, so now we just need to plug some things into our calculator and rearrange. So on the left-hand side, we should get a value of negative 33. And on the right-hand side, if I take 1 over 305 and then multiply that by 1 over 8.314, I get a value of 0.000394, and that is in, let's see, moles per joules. So that's going to flip the units there. And then if we solve for EA, we end up with 8.4 times 10 to the 4th joules per mole. And we can turn that into kilojoules by dividing by 1,000. And we should get a value of 84 kilojoules per mole. All right, so hopefully this showed you several different ways that we can use these Arrhenius equations in order to determine, for instance, an activation barrier or a frequency factor. But additionally, if we use the two-point form, we could solve for an unknown rate constant or an unknown temperature, as long as we have all of the other variables. So we'll stop there today, and next time we'll talk about the collision model or collision theory. So I will see you in the next video.